Today we're going to look at something called a normal approximation of a binomial distribution. For the binomial distribution. All right, so let's talk about these words for a little bit. First off, a normal distribution. This is the bell curve that we've been seeing so far in this, well, I guess in sections 9.3 only. This is a continuous distribution where we have a mean and we have, it falls off at a predictable rate. If you were to step one standard deviation off to the right, you can say, or if you're talking about the total area between one standard deviation to the left and one standard deviation to the right, this is something we can find. We would look at mu plus sigma. This would be mu minus sigma because this is one standard deviation to the left. And we could say, okay, what's the total area between these z values? Okay, so that's a that's the normal distribution. The binomial distribution, this looks a little bit different. This says if we have repeated trials with independent probabilities, or each of these trials are independent, I should say. Independent, yeah. And we're just counting the number of successes. Generally, when we're talking about a binomial distribution, we have a couple of different numbers. N is the number of trials. P is the probability of success. And X is the number of successes. All right, so you may be wondering what in the world does a normal approximation, or normal distribution rather, what does a normal distribution have to do with a binomial distribution? Okay, so where this comes in is when we start computing binomial probabilities. If we have large values of n, or let's just start with, in general, the way we compute a binomial probability, we say the probability that our random variable is equal to some specific value, we would find by doing a combination. So this would be n choose x, p to the x, 1 minus p to the n minus x. This is the actual formula that's used to compute this. Of course, usually we've been using the calculator to do this particular computation. But this is basically in the background what the calculator is doing, essentially what the calculator is doing. And you'll notice that this factorial right here, this is, in general, how we compute factorials. We would do them by, in general, n factorial, or n choose r, combinations, I'm saying factorials. We're using factorials to compute the combination, is what I meant to say. So n choose r, in general, is n factorial over r factorial, n minus r factorial. And these factorials get to be very large very quickly. For instance, 70 factorial, this is too large for your calculator. Let me just play around with that. So if I was to plug in, say, 50 factorial, my calculator can deal with it. It's a big number. You can see this is times 10 to the 64th power. But the calculator can deal with it. If I try to plug in 70 factorial, though, it's not that much bigger. It should be able to handle it, right? Nope. Error overflow. This is because it's bigger than 10 to the 100th. No, it's not 100 to the 100th. It's bigger than 10 to the 100th. And so the calculator just says, yeah, this is a big number. We're not going to deal with it. So this right here, when you start talking about large values of n, you can see that the numerator of this fraction ends up being an extremely large number. Each of these factorials end up potentially being large numbers as well. So we have some really large numbers floating around, and numbers that are potentially too large for the calculator to deal with. Not only that, when you take this power, when you take some probability, remember probabilities are always between 0 and 1, I guess less than or equal to, you raise some number that's between 0 and 1 to a very large power. Well, let's just try doing something like this. Let's do 0.5. 0.5 to the 10th. 10 is not that many trials, but if we're talking about that many successes, you can see this starts to get pretty small. You start doing something like 10 to the 1,000th, or 0.5 to the 1,000th. Well, the calculator doesn't know what to do with it. It just calls it 0. Basically, again, this is getting to be too small for the calculator to deal with. So simultaneously, when we start dealing with large values of n here, we start having simultaneously numbers that are too large for the calculator to deal with and numbers that are too small for the calculator to deal with. Well, these calculators do have ways of computing some of these things, like it can do, especially realizing that it's dealing with a binomial distribution, it gets a bit smarter than that. So you can actually deal with binomial distributions or binomial problems that have values larger than 70 in there. There's a lot of simplification you can do, essentially. But even so, it can start to take a while to do these individual distributions. So for instance, if I was to do something like Binomial Cdf with, let's say, 10,000 trials with a probability of success of 0.5, and let's say what's the probability of getting 500 or 5,000. So this would be if we're flipping a coin 10,000 times, what's the probability of getting 5,000 heads if it's a fair coin, exactly 50%. It didn't take very long there. Okay, so let's make the numbers a little bigger, since that one wasn't too hard for the calculator. So now let's look at 100,000 coin, flip a coin 100,000 times, try to find out the probability that it comes out heads exactly 50,000 times. Again, that's pretty fast, but you can see these probabilities are starting to get pretty small. If I kept increasing this, instead of 100,000, let's try 1,000,000. Well, okay, now the calculator's officially given up. It says, I've run out of tricks. I don't know how to deal with a million coin flips. So instead, yeah, like I said, the calculator is able to do, there's a lot of optimization that you can do with a problem like this, and obviously the calculator has utilized a lot of that. But you'll notice that these probabilities are getting pretty small. This is right at the expected value. You know, if you're flipping a coin 100,000 times, you would expect your expected value there, n times p, is 50,000. And you can see you have less than that's a 0.25% chance of getting 50,000 heads. And that kind of makes sense. You're likely to get, a little bit more or a little bit less, but you're going to be centered around that 50,000. So let's think about what happens when we start to talk about these large numbers of trials. So what I've done here is I've actually drawn out, or rather I've used my spreadsheet software to to show a distribution. So this is flipping a coin 15 times, and it's looking at the probabilities for each of these. You can see flipping the coin 15 times, we could get anywhere from 0 all the way up to 15. I guess this is heads, let's say. It doesn't really matter, it's symmetric. Could be heads or tails. But if you're flipping a coin 15 times, your number of heads could be anywhere in that range. And not unexpectedly, you can see it kind of peaks right in the middle. You get a roughly 20%, just slightly under 20% chance that you'll get 7 heads, or just slightly under 20% chance that you'll get 8 heads. Okay, that's not too bad. We could do this. We could say, what is the probability of getting exactly 7 heads or exactly 8 heads? We could do that. If we wanted to find a range of probabilities, what the calculator would end up having to do, let's say if we wanted to find the probability of getting between 4 and 9 heads. If you wanted to look at the probability of being within one of these values, getting 4, 5, 6, 7, 8, or 9 heads, the way the calculator would actually do it is you would use your Binomial Cdf, you would figure out the probabilities of all of these, and then you'd subtract off the probabilities of all of these, and then you'd get this number. Now the calculator, again, this does these things fairly quickly, so you could do that. You could do that without too much work, especially with flipping it 15 times is not that much for the calculator to deal with. But if we were to increase that to 100 times, and let's say I wanted to get the number of coin flips, I wanted to find the probability that I get between 40 and 60, let's say 40 and 55 heads, or 60 or something like that, you can see there's a lot more individual probabilities. And the way this calculator is doing this is it's finding the probability of each and every one of these. It might take the calculator a little bit of time. Actually, I don't know how long it'll take. Let's see. If I'm trying to find the probability of being between between 40 and 60 heads, then what I'd want to do is I'd want to do binomial Cdf. So I'm going to do the basically from here to the left. So that's going to be binomial Cdf. N is 100 because we're flipping the coin 100 times. The probability is 0.5 because it's a 50% chance. And we're saying getting at most 60 heads. So it would be that number. Then we want to subtract off. So this is from here all the way to the left. We want to subtract off the stuff over here. So I'm going to include 40 in this number. So I'm going to say minus binomial Cdf. I want to subtract off from here over. So if I'm including 40 in this range, the things that I'm counting, I'm going to start at 39 and less. So this will be 100.539. So I'm just going to see how long this takes my calculator to compute. Let's see, we want to go distributions, binomial Cdf, 100.560 minus binomial Cdf. I'm actually just curious. 100, oops, I opened up a second set of parentheses. 100, comma, 0.539. Okay, so that was actually still fairly quick. But you could see it definitely was starting to take the calculator a little bit of time, and that's because it was having to find this probability and add it to that one, and add it to that one, and add it to that one, and do all this, all the way down here, all the way down to 0. And then it was subtracting off this probability and add it to that one, and that one, and that one, all the way down to 0. You can see there's a lot of redundant work there. Not only that, when we start talking about increasing the size of n, not just a matter of redundant work, there's a lot of individual values we'd have to find. We'd have to find that one, and 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 add all those things together. So that's a lot of work. But you may have noticed the general shape of these distributions is looking a bit like a bell curve. So let's look back, going back to the n equals 15. Here I have an example of the normal distribution superimposed over this n equals 15. This is actually a chart I just pulled straight from the book. And you can see they actually do look substantially similar. Here's our normal distribution, and the boxes, these are this is the binomial. These are the exact numbers from the binomial distribution. Now, one way to look at this, remember with your normal distributions, you figured out your probability of being within a particular region with an area. You can actually think of that same way. Think of the areas of this, the areas of your chart representing the probabilities with these rectangles. As long as you expand them and have them a full width of 1, then the area of this rectangle here is the height times its width. Well, it has a width of 1, so the height times 1 is just its height. So the probability of this rectangle, the probability of getting exactly 7 heads is the area of this rectangle. I mean, it also happens to coincide to that height. But remember, with these continuous distributions, we always talk about the area underneath the curve, and that's how we end up getting our probabilities. So let's figure out how this would actually compare. Well, the area underneath this normal curve, well, I can't just take a single point. I have to take an area. I have to say you're going from one region to, or from one spot to another. And if you kind of look at what happened with these rectangles when I was counting this, I was going from, if I'm trying to find the probability of getting 7 heads, I'm kind of going from 6.5 heads to 7.5 heads. Now, of course, there's, the probability of getting 6.5 heads is 0, or the probability of getting anywhere between 6.5 and 6.9 heads is actually 0. You can get 7 heads or 6 heads. You can't get anywhere between them. But it doesn't actually change. If I was to kind of look at the area from here to here, it's all kind of gathered right at this spike, but it ends up, if you kind of count it as a rectangle, you end up getting the same thing. So what we're going to do with this normal distribution is do the same thing. We're going to say the area underneath this normal distribution for the approximate area, I guess, or the approximation of this probability would be just as if we're going from 6.5 up to 7.5 underneath the normal distribution. So, let's see, I actually have the values computed here. So the estimate, actually let's do the actual number here. If we're doing normal binomial PDF, n of 15 probability of 0.5 and x of 7, because we're trying to find out exactly 7 heads here, our calculator gives us 0.1964. I think that might be rounded. Let me actually go ahead and just do it here so we can see the exact value or see more accuracy. 15.57. We get 0.196386 whatever. So yeah, this is rounded, the 0.1964. Whatever, it's 4 decimal places. That's probably close enough. If we were to do the same sort of thing, going from 6.5 up to 7.5 with our normal distribution, then, I have it written here. You can see, remember with the normal CDF, we do the left bound, the right bound, then our mean, then our standard deviation. Oh, I guess I need to say what the standard deviation is. This particular curve, the way it ends up working, you say your mean is your expected value, which is going to just be n times p, and you would say your standard deviation, it's a little bit weird, but we're going to take the square root of n times p times 1 minus p. So a little bit of a weird calculation. But when we do that, n times p times 1 minus p, and we take the square root of it. So for our binomial distribution here, we take 15 times 0.5 times 1 minus 0.5, which is just 0.5 again. We get this number, take the square root of it, we get this 1.936. So that's where I got this standard deviation here. So here's our mean, here's our standard deviation. When we go to do this normal distribution, we'll go ahead and use those values. So that means I'm going to go into distributions. We're doing a normal CDF. My left bound is 6.5. My right bound is 7.5. My mean is 7.5. Yeah, my mean is 7.5. That's 15 times 0.5, n times p. And my standard deviation is 1.9365. You know what? I actually have it on the line just above, so I'm just going to say answer rather than typing it in. This is more accurate anyway. So when I go ahead and compute that, you can see I get 1.972. Or not 1.972, 0.1972. That's the area underneath this normal curve from here to here. So yes, they're not quite the exact same number, but it is a rather close approximation. And n equals 15 is actually kind of not that many trials. This approximation actually gets more accurate the more trials you have. So if you had 1,000 or 1,000,000 trials and you're trying to do it that way, you actually just end up getting more closer to the actual number.